Welcome to this explainer. Today, we're taking a seriously magical dive into a world where advanced mathematics and the wild, untamed beauty of nature completely collide. And the craziest part, it's happening right there in the produce aisle of your local grocery store. So get ready, because we are tumbling straight down the mathematical rabbit hole.
Now take a look at this. This is the Romanesco broccoli. Technically, it's a variety of Brassica oleracea, which, believe it or not, makes it a close relative of your everyday cabbage, cauliflower, and Brussels sprouts. But, come on, it definitely doesn't look like an ordinary cabbage, does it? With these bizarre, otherworldly, lime green spiral structures, it looks way more like an alien artifact or some master sculptor's intricately carved art piece. It is just this stunning visual mashup of math, nature, and art, all rolled into a single living organism.
Okay, let's really dive into this. When you look at those mesmerizing peaks and perfectly twisting spirals, you kind of have to ask yourself, did a mathematician actually design this vegetable? Well, while chefs might prize it for its delightfully nutty flavor, mathematicians, they are utterly obsessed with it for a completely different reason. You see, this seemingly ordinary plant holds these profound, ancient secrets of algebra and geometry locked right inside its leaves.
Part 1. Nature's Secret Algebraic Code. So to understand how this is even possible, let's transition a bit deeper down the rabbit hole and uncover the very first hidden mathematical law governing our captivating vegetable here. We're talking about the famous Fibonacci sequence. The steps to build it are beautifully simple. You literally just start with the numbers 0 and 1. Then you add the last two numbers together to get the next one. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, then 5, 8, 13, 21, 34, and it just repeats like that endlessly. Now, a mathematician named Leonardo of Pisa, who is famously nicknamed Fibonacci, actually wrote this sequence down way back in the year 1202. But here is the really incredible truth. Nature had already been using this exact algebraic code for millions of years before humans ever figured it out.
Just look at the abstract Fibonacci spirals on the left and compare them to the real Romanesco head on the right. If you were to sit down and count the spirals winding clockwise on a typical Romanesco, you would find exactly 13 of them. And if you count the spirals twisting counterclockwise, you'll find exactly 8. 8 and 13. Think back to that sequence we just talked about. Those are consecutive Fibonacci numbers. Guys, this is absolutely not a coincidence. It's an exact mathematical law playing out directly in biology.
Part 2. Geometry of the golden angle. Oh, okay, so that covers the algebraic pattern. But how does the plant physically build these perfect numerical spirals as it grows? We're shifting our explainer now from algebra over to geometry. Enter the golden ratio, which is often represented by the Greek letter phi. As you advance further along that Fibonacci sequence we just looked at, if you divide a number by the one immediately preceding it, say 13 divided by 8 or 34 divided by 21, the result magically converges on this exact, incredibly beautiful decimal, 1.618. This ratio is known as the most beautiful number in mathematics, and it literally dictates the fundamental geometry of the Romanesco.
So how exactly does this abstract number manifest in a physical vegetable? Well, it translates into something called the golden angle. Deep at the very center of the Romanesco, there's this tiny zone of growing cells called the meristem. This growing tip releases a hormone called auxin. Now, to avoid the high concentration of auxin from the older previous buds, each completely new plant bud is forced to sprout at an angle of exactly 137.5 degrees away from the last one. And that number, 137.5 degrees, it is driven purely by the math of the golden ratio.
But here is the absolutely crucial point. Why does this specific angle matter so much? Why 137.5 degrees? Well, because it's one of the most mathematically irrational angles possible. Think about it. If the plant simply grew leaves every 90 degrees, every fourth leaf would perfectly overlap and shade the ones directly below it. But because 137.5 is so extremely irrational, no two leaves will ever perfectly align, no matter how many leaves the plant grows. This guarantees the plant captures the absolute maximum amount of sunlight for ultimate survival. Nature is literally using complex geometry to stay alive. How cool is that?
Part 3. Tumbling into infinite fractals.
Oh, we are definitely not stopping there. We're zooming even deeper into the rabbit hole now, moving to a place where geometry transforms into a mind-bending, infinite biological masterpiece. Let's talk about fractals. A fractal is essentially a shape that displays self-similarity. And what that really means is, no matter how much you zoom in on the shape, the exact same pattern repeats at every single scale.
So we're moving away from the hard equations here for a second and focusing purely on the visual art of infinite self-repeating patterns.
And as you can see, this brilliantly illustrates exactly what we mean. Just look at this progression. We start with the whole Romanesco head at roughly 10 centimeters. But if you break off just one single floret at, say, 3 centimeters, it's a tiny, perfect replica of the entire head. Break a piece off of that floret down to 1 centimeter, and you still have an exact miniature replica. The self-similarity just keeps going. Every single scale looks exactly the same.
Now, just to ground this whole surreal journey through Wonderland into actual hard science, listen to this quote from Dr. Zachary Stansel over at Cornell University. He says, "Romanesco is thought of as the quintessential model of fractal architecture in biology." So, this isn't just some fun visual trick. It's genuinely recognized by biological authorities as a total pinnacle of natural fractal architecture.
Part 4. Biology's ultimate mathematical masterpiece.
All right, let's tie this entire explainer together. We've woven through the algebra of Fibonacci, the geometry of the golden ratio, the visual art of fractals, and the biology of plant survival. Just think for a second about human engineering versus biological engineering. For humans to create fractal art or perfectly proportioned architecture, we have to painstakingly calculate the geometry using supercomputers and advanced tools. But nature simply relies on the automatic spacing rules of a basic hormone called auxin to effortlessly, and I mean completely automatically, grow infinite mathematical perfection. Biology is, for sure, the ultimate effortless artist.
It really all comes back to the single, breathtaking image. Math, nature, and art coexisting flawlessly. This incredible approximate fractal, governed by phi and the Fibonacci sequence, it isn't locked away in some high-security museum or hidden in a dusty math textbook. It's something you can literally buy at the grocery store, hold in your hands, and eat for dinner. It's just wild.
Which really leaves us with one final awe-inspiring question. If a simple vegetable holds the infinite geometry of the universe, the very mathematical codes that shape galaxies and hurricanes, what else are we casually walking past every single day? Thank you so much for joining me on this explainer. Keep your eyes open out there, because the math, it is everywhere.